Welcome to Alchemy Wizard. I'm Tom. Today, Magnesium 2.0 with the plasma arc. Some metals are harder to create colloidal nanoparticles out of than other metals, and it depends on the process involved too. Some metals don't work with one process. Some metals work with all three processes. We got low voltage electrolysis, we got plasma arc, which uses 15,000 volts of electricity, and we got now the laser setup for creating laser. So this segment is on Magnesium 2.0 with the plasma arc. Now, magnesium is a really tough metal to make a colloidal out of. In low voltage electrolysis, you might get a few colloidals in there. Actually, in plasma arc, we don't even get any colloidals in plasma arc at all. What we managed to get is just magnesium dust. So we need a way to create plasma arc magnesium. And we have a way of doing it. It involves weird science, as I'd like to call it. And we've done this already with other metals. It only really works with plasma arc. But basically, instead of using two magnesium rods in here, we're going to use a titanium rod and we're going to use a magnesium rod. Now, the theory here is that the dissimilar metals will help create a stable magnesium. Magnesium isn't a very complex metal, and as such, it doesn't have if you want the geek speak on it, the protons inside magnesium don't have a lot of force to them, and this is why magnesium is tough to create a colloidal on in any method, because there's so little protons in there. When we create these colloidals, they can't stay together. There's not enough van der Waals energy holding them together, and they fall apart. Magnesium is roughly a very soft metal, and titanium is a hard metal. So, in theory, we're going to get lots of magnesium material in there and not a lot of titanium material. But we need some titanium material in there because we want the titanium atoms, the protons from the titanium atoms, to bind with the magnesium atoms so we get a more stable colloidal out of the magnesium. So in essence, let's say we'd have one titanium atom and 100 magnesium atoms all bonded together to create a magnesium nanoparticle with just a hint of titanium in there. The titanium forces are much stronger in the atom, in the nucleus of the atom, than they are in magnesium. And this actually does work. We've done it with other metals. Now, it doesn't always work with every metal. Titanium isn't your go-to guy. I don't forget which one it is, but one of the metals that I've used is this similar technique with. I've used stainless steel because the titanium wouldn't work. It has to be the right combination of metals. And the only way to really figure that out right now is through trial and error. So the first thing I have to do, as far as the research end of it, is to make sure that we don't get a lot of the titanium material and more of the magnesium material. So I put it in the scale over there and I weigh both of these metals so I know exactly how much material we have now, and I will weigh them again afterwards to see how much material we have after. If done right, we'll lose virtually nothing off of the titanium and maybe something off of a milligram or two off of the magnesium. Now, the way I've made this magnesium rod is I took two of the flat stuff, the flat magnesium stuff, and I twisted them together to create a wire-like substance. Now I'm going to put them in here and adjust them, get the right gap, and then I'm going to go through the plasma arc process. Magnesium is a tricky process. You have to keep moving the magnesium closer and closer as it burns down, because the magnesium burns fairly quickly. And I like to keep it going until I can't get any more magnesium into the solution, where the arc just kind of goes out. So We're at 8 minutes. Tell you what, let's talk about the setup a little bit. We've got 15,000 volts coming in on the top here. And this shield, this black shield here, has got magnets on it. And the magnets help create stronger colloidal nanoparticles. They also help block the EM energy from going too far. The magnets kind of contain the EM energy. The little door here is I will rotate this over here towards the camera, and I will watch through the camera to see if the arc is still going. Now this arc is kind of small, but it started out like a brilliant flare. So you can't really watch the arc without glasses, and I don't even like to be staring at the arc too long, even with the glasses. I mean, if some of the arcs are so bright, magnesium in particular, that I'll use these things, the welding goggles. Okay, we are finished with the cooking process, which took 46 minutes roughly. That's the picture over there. Give you a big up version of it too as well. I measured out the rods, okay, and it's important to note when you're measuring magnesium rods, they have to dry out. Magnesium is a soft metal and it will absorb the water and act as a sponge. And actually, when you go to measure the magnesium rods, after you've just pulled them out of the water, they actually will be heavier than when you started. So let your rods dry out for at least an hour before you take the final measurements, if you're measuring your rods. So that's only important in knowing if we got the right balance with the solution. Okay, the amount of material used is 1.9 milligrams of magnesium and 300 micrograms of titanium. As far as I'm concerned, it's colloidal magnesium. With that % titanium, bonding with those magnesium atoms is enough to create a lot of colloidals. I mean, almost 20 parts per million solution colloidal magnesium is really phenomenal. So that's how we make magnesium 2.0 with plasma arc. I'm Tom, Alchemy Wizard. I'll talk to all of you again soon.